Hello. Welcome everyone for the first session. So we have our first speaker, Duvenaud from University of Toronto, and who is currently an assistant professor. And the talk title is Self-Tuning Gradient Estimators for Discrete Random Variables. Welcome, David.
All right, thank you, Shane. Okay, so we have a complicated microphone setup. So first thing is, can everyone hear me now? Okay, and the mic is helping? Okay. All right, let's, oh no. Okay, so the title of the paper that this work was based on has a much more evocative title, which is called Backpropagation Through the Void. Because we are going to give gradient estimators when functions are even unknown that we want to optimize. But I want to say that this is such an awesome venue, and it kind of makes me think of like how like the Edinburgh Fringe started, like when there was too many shows for that thing. So maybe this is going to grow. So the overall setting that we want to address in this paper is we want to optimize some expectation under some random variable of a function. And I realize this might sound too broad, and I would say exactly, this is amazing. We're going to talk about a new technique that we can use in this setting pretty much without restriction. So where we do see this, for the purposes of this workshop, is variational inference, where this expectation might be, the expectation under the Q distribution of a, log likelihood plus KL or something like that. Maybe we're doing Hamiltonian Monte Carlo, and this is just the unnormalized log density, and maybe B is like a discrete random variable or something. We're doing Bernoulli, like binary logistic regression or something. This is also the framework of model-free reinforcement learning, where F is like the reward function, beta is the policy, and B is maybe some actions or a whole trajectory. And finally, people also have been talking about adding like hard attention for models like neural Turing machine, the discrete neural Turing machine, and then trying to optimize stochastic policies to guide their hard attention models. Okay. So when I started my PhD, I was firmly of the belief that we shouldn't just throw things into some gradient descent, or even worse, some sort of like reinforcement learning setup that ignores the structure of the problem and doesn't reuse all of our old observations. And worked on Bayesian optimization for a while. And then eventually was disillusioned. And I think my current take is basically that it would be amazing if we could, coherently reason about all the function evaluations we've made so far and optimally choose the next point to evaluate next. But our models, like Gaussian processes, although there's been a huge amount of progress in the past few years, and I might have to revisit this assumption, still aren't quite up to the task to cheaply reasoning in high dimensions about some global, the function that we're trying to optimize everywhere. So, and it's kind of weird. I kind of watched with embarrassment at how successful all the deep reinforcement learning demos were, and I realized that they were settings where you have sort of unlimited access to the function you're trying to optimize. There's not really much generalization going on, but still, it seemed like just doing this like black box gradient-based optimization that doesn't even use gradients of the function you're optimizing, just using something like reinforce, was sort of like an embarrassing state for the field to be in almost, and for that to be the state of the art. Although I think that's changing soon. So the basic idea of this talk is going to be, can we add some sort of cheap or local model-based optimization to something like reinforce and have a cheap and cheerful sort of model-based optimization that doesn't require us to really reason in a coherent way about the entire objective that we're optimizing, but still is as applicable everywhere as reinforce. So just so that everyone knows what I'm talking about when I say reinforce, I just mean the score function estimator, aka, introduced by Williams in 1992, who also actually introduced the reparameterization trick in that paper, but it's sort of buried. So we're just going to, it's like the do what feels good more estimator that says, if my function was high, then I should take a step in the direction that will make me more likely to sample that value of B again. Okay. And this is an amazing estimator because it's unbiased, so we can just average as many samples as we need, and it works for any F, even if it's not differentiable, or even if we don't know what it is, and it's a literal black box like an Atari console or something like that. And of course, it just, in general, has very high variance. And we can sort of see why, which is that it's not exploiting any structure of the function being optimized. All it, we bake an entire batch of cookies, and then at the end we just find out like what our overall rating for it is, and we don't know anything about gastronomy or human physiology. We just, do more of what works before. Okay, so for this talk, my student Jesse heroically made some really nice visual demos, actually visualizing these different algorithms in action. So here is reinforce, optimizing the mean of a Gaussian. So the green thing here is a Gaussian, and the wiggly blue thing is F. And we want to maximize the expectation of F under this green thing, only optimizing the mean. If we optimize the variance, we'd end up with this pathological thing where we want to shrink the variance to 0. Okay, and we really should be showing you the variance of the gradient estimates. So it looks like it got there really quickly, but actually it was just guessed right. There's only 2 directions you can go. The variance is so high here that we had to turn up the momentum so that it didn't just bounce around and diverge. And what the optimizer is doing is not all that closely related to what the maximum of the function is. And this makes sense because all the estimator can do is basically say, if I got a high value, move my parameter more in that direction. So it's relying on averaging the function evaluations that happen sort of on the left side of the curve against the ones that happen on the right side of the curve. Okay. So now, obviously, the sort of gold standard, at least we think, is the reparameterization trick that was really popularized by the variational autoencoder papers that says, oh, well, don't use square function estimator. Try to find a way to differentiate through F, right? This is going to be very powerful because it actually exposes the dependency of the output to its input in a really detailed way that will scale to high dimensions. So it usually has lower variance, but there's no guarantee here. There's some toy analyses we can do, but it is unbiased, and it is what allowed people to train very large continuous models like BAEs for the first time. Of course, we need F to be differentiable, and we need to find some sort of reparameterization, and we're going to hear more about that today. So here is reparameterization trick being used to estimate gradients with respect to the mean of this distribution, and normally this would work actually very well, but we've chosen a sort of pathological F, this very wiggly function, such that the reparameterization gradients doesn't really tell us much about the overall shape of the function. So what this is doing is sampling from this Gaussian, and at each point, evaluating the function at that point, asking for its gradient, which has this sort of very high variance sinusoid added onto it. So, normally I would definitely recommend if you can use reparameterization trick, you're probably in good shape. But here's an example where it fails. Okay, and this only applies to discrete variables, but obviously we all know about the Gumbel softmax concrete trick, which basically says, well, let's not differentiate the original function. Let's build a relaxed surrogate that doesn't necessarily have anything to do with the original function that we're trying to optimize, and sample from a different distribution, and sort of hope that this has low enough bias that it's useful. So I didn't quite get this, I think, clearly from the first few times I read the paper, that this is just a function you can differentiate that might have something to do with the function that you want to optimize. And it works well in practice, so we can't bash it too much. It is biased, but we can tune the parameter to reduce the variance at the cost of increasing the bias. But to me, the weirdest thing about this method is that it uses undefined behavior of f of b. So in the discrete case, b is a discrete variable, and f really only needs to be defined at at these discrete inputs. And what we're going to do is feed it some continuous inputs in between the sort of edges of the simplex, if you want to think about it that way. But the funny thing is that there's uncountably many ways that I could define f in between the corners of the simplex that would give me the same expectation that I want to optimize, but would give me different relaxations for the concrete trick. So that might be a good thing, then we have another knob to tune. But I just want to sort of highlight that that's sort of a funny thing about this approach. It works really well. Finally, the last thing we can do to build gradient estimators, and this is just a general trick, is to introduce a control variable. And all that means is we take our original estimator g hat and introduce some function c. And we're allowed for c to depend on the variable that we're sampling if we add back its expectation or some unbiased estimator of its expectation. And of course, this may sometimes hurts, sometimes helps. It helps when our control variant is correlated with our original estimator. And that looks good, but the problem with using this in practice is that if I'm optimizing my problem, at every iteration it's actually a different estimator that I'm trying to be a control variant for. So I can't, and it's usually expensive to build a gradient estimator that's correlated with whatever estimator you're trying to estimate. So you have to somehow adapt G as the problem changes. So you can't use the exact optimal control variant, even though it has like nice formulas for it. Okay, so without further ado, here is the approach in our paper, and it's, I think, delightfully simple. And we got from working backwards from the rebar paper to a sort of simpler solution. So we're going to say that the lapse estimator takes some, and this is for gradient estimators, by the way. So G is, okay. So we're going to be wanting to optimize or find gradients of f with respect to some function. So we're going to build a reinforced estimator, and I'll put this more precisely in a second. We're going to build a surrogate function c, which has the same type as f. And we're going to build a control variant that just says, okay, use reinforce to estimate the gradients of c with respect to the same parameters, and then add back the gradient you would get from using the reparameterization trick on our surrogate. So again, f isn't necessarily differentiable or even known. C is maybe like a neural network that we're going to learn. So we can differentiate it. And we normally never use the score function estimator on a neural network, because why would you? You have the reparameterization estimator, but you can use it. So just to spell this out a little bit more, so I've actually confusingly grouped two terms now, I realize. But so the reinforce of f is going to give us this term and that term. Reinforce of c is going to give us that term and that term. And then so this is sort of like the crappy reinforce-based gradient estimator. And this is going to be the nice reparameterization estimator that we're going to hope is low variance. So the idea is that if c looks a lot like f, then these two terms will cancel out, and our high variance guy will go away, and we'll be left only with our beautiful low variance reparameterization estimator. Okay, so this is a histogram drawn from one of the experiments with VAEs from our paper, showing the actual gradient estimates for a single parameter using this estimator after we've, in the middle of training. So the idea is that reinforce, yeah, it's unbiased and it has this high variance. Reinforce on our surrogate has bias because it's, the gradients of a different function, but high variance gradients. And then our reparameterization gradient does, in fact, have very low variance. But it's always good to check. I really don't like drawing conceptual figures. I always try to make real, demonstrations, because sometimes I'm wrong, and the reason why I thought this thing worked isn't the case. But here it is. And the missing part that it's hard to show is that these guys are very highly correlated, so they cancel out. So when we add all these terms together, we get something that is unbiased and has about as low variance as the reparameterization estimator. Okay. One thing I want to mention about this gradient estimator is that if c equals f, so if we learned our control variant really well, then these two terms would actually cancel out exactly, and we'd be left with just purely the reparameterization gradient estimator. And that's without having to differentiate through f, right? If we can learn f in a roundabout way, then we can use the reparameterization trick again. Astoundingly, this isn't always the minimum variance form of C. Sometimes we can have a gradient estimator that's even lower variance than the reparameterization trick. Okay, so what this looks like, so the missing piece is how do we optimize C? And there's sort of only two things we can care about. One is the bias of our estimator, and the other one is our variance. We want low variance, so let's just directly differentiate the variance and take a step in that direction. So we're just going to try to directly minimize the variance of our gradient estimator. And what lets us do this is a beautiful identity that I think was independently discovered by Frank Ruiz and David Bly's group in their over-dispersed variation inference paper, and then in the rebar paper also. They derived this nice identity that says that if you have an unbiased estimator, the gradient of the variance is actually just the expected gradient of the squared norm of the original gradient estimator. So basically, if our gradient estimator is unbiased, making it smaller has to reduce its variance and it can't not be unbiased, so it doesn't matter, what we do. So we use this to optimize our surrogate, but even if we haven't optimized our surrogate, everything is still unbiased, and we're still taking steps in the right direction on average. Okay, so this is sort of one of the main ideas of the talk. So, actually, I'll show a demo and then I'll ask questions. So what we're going to do is say, you could first optimize the surrogate and then optimize, but why don't we just throw it all in a giant soup of gradient-based optimization? So the algorithm basically says, do the lax update, which is the same formula I showed before, then do this gradient through the gradient estimator, and then update the original parameters and the surrogate. So just throw it all in a pot and let atoms do it. Okay, so here is lax now solving the same problem that we showed before, and here is the control variable that's randomly initialized and is going to be adapting as we optimize to reduce the variance of the lax gradient estimator. So, so the thing is that I still don't have a great understanding of what optimal control variables in this formulation look like. And it should actually be a fairly simple exercise for some toy problem to just do the variational calculus to find the minimum variance control variable in closed form. I've actually given this to a few students, and no one's ever managed to do it, and I know it has to be pretty straightforward. Anyway, I say that, I didn't get it to myself though. Okay, so this is sort of the main recipe of the all the algorithms we're going to build on for the rest of the talk. So I want to stop here and answer any conceptual questions if it's confusing what we're doing still. Any questions? Yep.
I have one question just about the setup of the problem. So I know that the objective function is kind of the expectation under that distribution that you're plotting of that really wiggly function. And I know that must be a smooth version, but does it have any local optima or not?
Oh, that's a good question.
Could, right?
Yes. So actually, there's no reason why we couldn't have plotted the actually smooth objective as a function of the mean in this example. That's a great point. And you're right, depending on the relative ratio of the small wiggles to the Gaussian, this may or may not have local optima. Yeah. I guess I would say that in my mind, local optima aren't a problem in high dimensions. And so I don't really worry about it in this instance. Okay, other questions? Yeah.
So is there a guarantee to converge to a local optima? You're optimizing over two different things.
Yeah, that's a great question too. So are we guaranteed to converge to a local optimum because we're optimizing over two different things? And I haven't thought about it. My instinct is that if we take small enough steps in both settings, we will. But there's been awesome work by, for instance, Sebastian on GAN training, and it's not actually always the case that if you just take small enough steps, you do generally converge. That's a really good question. Okay, so how are we doing for time? All right. So now what I said we were here for is discrete variables. Right. This last estimator I've shown you is just for continuous variables, just because it's easy to make plots and movies and things for continuous variables. I find it always punishing to read papers about discrete variable estimators because there's never any figures. But here we go. So what is the version of lax for discrete variables? So the simplest version, we call it dlax, and it has pretty much the same form. But we have to distinguish now between our continuous noise, which we'll call Z, and the discrete variable, which is B. And the point is that we can only feed B into F. So this is just the standard reinforced estimator for B. And then now we're going to use reinforce on C, but C gets to take the continuous version of the noise, right? So this is like the Gumbel noise or something like that, some sort of relaxed version of B that we can turn into a sample from our discrete distribution by using some Heaviside function or step function, something like that. So we still have now reinforce minus expectation or minus reparameterization, but just of a slightly different variable than the original function. And of course, this is still unbiased. These two things cancel out an expectation still. Okay, so we call this dlax, and again, it's unbiased for LC, and we can use all the same tricks. And then there's this trick from the Rebar paper that said, well, I don't know. I still don't think this intuition is very straightforward. That basically says that we never expect to be able to sort of cancel out these variables as well as we can in the continuous setting. So there's this refinement that says oh, we have to introduce a second z tilde, which is, okay, we sample our previous z, sample our discrete variable based on that, then we resample the noise conditioned on having chosen that discrete variable. And so this is kind of like the refined noise estimate conditioned on having, on the particular discrete variable that we've chosen. And if anyone can give like a really concise explanation for the intuition for why this is a good one, please pass it along. But yeah, this is sort of, in practice, lower variance estimator. The real reason why we wrote the whole paper about this version of relax and not delax is because when we wrote the paper, rebar was the state of the art, and we wanted to only change one thing and not, have to do another set of experiments. So we said, well, we agree with their intuition that this refinement makes sense, so we're just going to start our experiments at that point. Yeah, so the whole, a lot of the ideas in this talk were actually developed by the rebar paper, right? Like introducing, well, optimizing they optimize only the temperature of gumball softmaps to minimize the variance, but same idea is with. So the genesis of this paper was reading the rebar paper and saying, wait, all of their identities go through no matter what the relaxation is. In fact, it doesn't even have to be rebar or the concrete distribution, it could just be any function f. So let's just do that instead. So in particular, so rebar is a special case of relax where we use the concrete relaxation as our surrogate C. And now, the other sort of technical step was to use automatic differentiation to do the gradient through the gradient estimator to tune the all the parameters of our neural network and not just the one temperature parameter. Okay, any questions at this point? All right. So now we're going to say that instead of rebar, which takes this one sort of form of a relaxation and tunes one parameter of it, we're going to have a free-form relaxation. So we're going to take the toy example from their paper to show that we're not cherry picking and actually crank up the difficulty. So this problem says that there's like a parabola that's like slightly off center. We're going to try to optimize the expectation of it. The right answer is basically to go to the one side of to always sample from the one side of the parabola that's a little bit higher. And of course, it's a Bernoulli problem, so it doesn't actually matter what the shape of the function is in between. We're going to show that it's, that's a weird thing about rebar is that it does depend on the shape of the function in between its discrete inputs. So how well it works here. So on the left here is the loss on this problem, and we're going to compare reinforce, rebar, relax, and the exact gradient that you can just get by summing, zero, the function at 0 and the function at 1. And so, we should have actually averaged this over many runs in retrospect. But the point is that, reinforce and rebar in this setting have very low, or very high variance. Even though they're both unbiased, so they both kind of wander around. We can get sort of a lower bound on how well we could ever do with the exact gradient, which gets there pretty quick. And relax is, doing pretty good. And then, our explanation for why this is happening is because we have lower variance, which we do when we actually, measure the variance empirically. So one funny thing here is that the variance kind of goes up and down. And my guess for why that's happening is that when we update the parameters of our model, again, we're changing the problem that we're optimizing. So the surrogate, the optimal surrogate is now different, so we have to sort of spend some time to catch up. So there's this kind of, I think, unfortunate leapfrog dynamic, or you can call it leapfrog dynamics, where we make progress on the problem, suddenly we're in a new sort of landscape. We need to optimize our surrogate, but again, before we're going to make much progress. But that's better than not optimizing the surrogate at all. Okay, so what do these surrogates look like in the discrete case? So for this particular example, again, where the original function is just a parabola, we can say what does the function we're feeding into reinforce look like as a function of our uniform noise that gets transformed by all these different methods into the discrete random variable. So reinforce obviously just looks like a step function. It gives us one gradient estimate if we guessed sort of 0 and one if another if we guessed 1. Rebar has to relax this parabola by putting it through a sigmoid. So its functional form looks like this sort of funny warped parabola, and relaxed, well, it kind of looks like a relaxed version of reinforce. That's sort of where we got the name from. And the funny thing is that you might say, well, what if I made C look exactly like f, maybe that would be the optimal surrogate, the kind of things we cancel out. And actually, that's not the case. We would get infinite variance. So we know, I'll assert that the optimal surrogate is always smooth, even in the discrete setting. It's always going to look sort of like a relaxed thing. Okay. So one kind of aside is that when you try to implement this, it's a complete pain in the ass. This is me using AutoGrad, which is the like Harvard AutoDiff framework that doesn't have GPU support, but is otherwise very nice, to define relax. And it's very nice, and we can just write down the functions like the surrogate is a neural network. We just kind of like sum up the different parts of the estimator. It's all very nice. And I want to say it's nice because AutoGrad lets you define functions and derivatives with respect to functions, and not computation graphs, and then all this stop gradient nonsense that gets especially hairy when you have to do higher order derivatives. So my student Bill Grathwell heroically translated this into like 800 lines of TensorFlow, and it was a nightmare. Also, one thing that neither TensorFlow nor AutoGrad do very well is per instance gradients. Like normally we just get the gradient of the sum over a mini batch, and that's actually hard in every framework except for JAX. So this is like something that is like just sort of been secretly released by Matt Johnson and do Google at Google. You guys should check it out. I think I've been meaning to rewrite relaxed in JAX. I think it's going to be much simpler and faster. Anyway, the overall takeaway is please don't use computation graphs to reason about higher order derivatives. Functions are just, they do the job. Okay, so one thing we applied this to was discrete variational automobilers. Mainly, again, because the rebar paper did this, and we wanted to show that we weren't cherry-picking our problems. So here is our L of theta, which is just the entire, the variational elbow. And the latent state is 200 Bernoullis, so we can't use the reparameterization trick that let us train VADs in the first place. So one really great thing about rebar is that it uses our knowledge of the function. So for reinforcement learning sort of things, we obviously can't use rebar. But if we're optimizing a model, we shouldn't throw away all our knowledge of like the function and how things depend on each other. So you could say that would be a reason to use rebar instead of relax. Because relax has to learn everything from scratch, right? It doesn't initially know anything about the function you're optimizing. So I just want to point out that there's no reason why you can't use both. So you can just say that my control variate is, my original function fed some Gumbel noise, Gumbel softmax noise, and plus some neural network. And so we can sort of start with rebar and then let relax clean it up. And yeah, it did pretty well. So actually, I don't know, the difference wasn't astounding, but it's always in the right direction for this instance. And we actually had a big debate about whether it was more important to report training error or validation. And I'm a big believer that we should make our optimizers optimize and our regularizers regularize. And if we shouldn't criticize an optimizer for overfitting, it's like saying that this car goes too fast, so it was crash. No, you just need better brakes. Okay, and then the very last part of this talk is, I know that we're in the AAVI workshop, but this is an instance where thinking about approximate Bayesian inference led us to a better reinforcement learning algorithm. So as I was mentioning, you can't use rebar for functions where you don't know what the function is, right? So if it's an actual black box, we don't know how to do Gumbel softmax through an Atari or something. But with relax, we just have this free-form estimator that we differentiate through, so we can actually use it for model-free reinforcement learning, which I know I've said is overhyped, and I think that's true. But I still want to talk about this. So here is the sort of unrolled through time reinforce estimator. It's like sort of people call it falsely gradient. And often people say, oh, we should have a baseline of, given the state, what is our sort of like expected reward that will reduce the variance? And there's like this holy grail of can we have action-dependent baselines, right? Can this C depend on action and state? And in general, the answer is no, because that would introduce bias. So what we can do now that we have lax, or this whole set of tricks, is to say, yeah, we can add action dependence. We just now need to differentiate through our surrogate and get the control variate again. And this actually does look pretty close to a lot of stuff that people do in reinforcement learning, and then they'll just, well, let me say, the really nice, yeah. So this happened contemporaneously with a bunch of work that did also figure out ways to put actions in the baseline. And I'll just say that now, this method still stands alone in directly minimizing the variance of this estimator, instead of introducing, or rather, the standard way that this was done was to say, oh, let's just do ordinary least squares and try to estimate, or minimize the squared error between the actual return reward and our estimate. Okay, so here's our model 3 RL results. But there's sort of, well, I want to say that, we converge faster, like in the inverted pendulum. But I'd say the real story is that because we have unbiased estimates for the control variate, this leads to stabler training. However, there was this awesome follow-up paper to this and a few other works, the Mirage of Action-Dependent Baselines in Reinforcement Learning by George Tucker and some other people here, who basically pointed out that having added this larger control variate gave our model a bunch more parameters. So if we wanted to sort of isolate the variance reduction as a contributor to the improvements in performance, we would have to try like much larger action spaces, which we haven't done yet. So please take this with a grain of salt. Like this isn't like, I think, damning, but I'm really happy they wrote this paper, and I think that was really, on the nose, or valid criticism. Okay, so I talked about all these other gradient estimators, and just to sum up, so relax is unbiased always, and has lower variance after you tune the surrogate a while. We can use it even when f is unknown, so that's why we call it backdrop through the void, and when we have discrete inputs. And the cons are, well, we have to define the surrogate, so now you have another model selection problem. Again, there's this funny thing where if you do make a lot of progress, you have to wait for the surrogate to adapt before you make more progress, although that, the optimizer takes care of that. And actually implementing these higher order derivatives is still a little bit awkward in our current tools, besides JAX. So just sort of zooming out a little bit, I think that if we want to do something, we don't have to do whole hog Bayesian optimization, we can just introduce local surrogates. And this is sort of much less demanding to construct and fit and reason about. And if you want low variance, use this trick from Frank and the rebar guys that you can just take the gradient of your variance sometimes. One aside I want to give is, I don't know if you guys followed evolution strategies. I was also very sad to see evolutionary methods make come back. I mean, it's just like this random search thing. So one funny identity, this is unpublished, but it's not that newsworthy, I think, but it's that the actual gradient estimator that, the gradient estimator that evolution strategies uses is actually the same up to one expectation of the covariance matrix as ordinary least squares. So you can say evolution strategies, puts down a bunch of samples, evaluates the function, fits a linear surrogate, takes one step in that direction, then throws it all away. A couple of my students played around with, well, why don't we just fit a neural network there and use old samples and things like that. But ultimately, I don't like using random search at all, so I wasn't really that excited about this direction. Okay. So, future work is basically, can we do some analysis on the optimal surrogate? Should be easy in principle. We can also make the policy a function of the current parameters of the function we're optimizing, so that if we happen to come back to a new, so this pi that's the policy, that could also be theta. So as we tune our model, we can say, oh, the optimal policy has been changing in this particular way for the last 3 model updates. Maybe we can sort of extrapolate. And there's been all this amazing work on finding nice relaxations for things like trees or permutations. The big weakness of this approach, when I wanted to apply to something interesting, is that it's not clear how to build good surrogates when we have a sequence of discrete choices, like a list of a length that's random or a tree that has a random shape. That's sort of very ugly to deal with very quickly. Okay, thank you very much.
We may have time for 1 or 2 questions. Is there any questions? Maybe Marie also set up the presentation. So question from the audience. I think it's very cool that you also presented this use case in reinforcement learning. So I also want to get to know your opinion in general. for operational inference and recursive learning. Like, what do you think is a common ground that we can do research together?
Oh, well, actually, it's really funny because for the last like 3 or 4 years, I've been saying, oh, model-free reinforcement learning won't stand the test of time. It's not data efficient. We need to move to model-based reinforcement learning. So, but then we wrote this paper and we said, hey, we have a new model-free reinforcement learning algorithm. That's cool. And then Will Grafwell, I don't know if he's here, the first author, actually was in Berkeley for the summer, and he gave a talk at the, to give Levine and Peter Beal's group about this work, saying, hey guys, it's like a really principled, nice way to set up model-free reinforcement learning. And they were like, oh yeah, we don't care about that anymore. We've all moved to the model base. So